In this lecture, we're going to talk about the Bohr model and how we can use that to explain atomic line spectra. So we'll start off learning about the Bohr model of the hydrogen atom and talking about what orbits and energies are allowed and how you can use that model to describe absorption and emission of light. And from that, we'll be able to explain the atomic spectra. So as we saw in an earlier lecture, atoms can emit light at certain distinct wavelengths. These are the atomic line spectra. And these emission spectra provide a fingerprint for that element. And as we said before, classical physics can't describe why we get just these discrete emission lines. And so our goal here is to build a model that describes these features and can explain why these lines occur at the particular places they do. And in particular, we're going to be focusing on the hydrogen atom. So around 1920, Niels Bohr was working to try to understand the hydrogen atom. So at this time, Rutherford's gold foil experiments had already been done, and so there was already this understanding that the atom had a positively charged nucleus with electrons moving around it. So a general idea for the atom was something like the planetary model of the atom, where you have electrons orbiting like planets around the nucleus, which is sort of like the sun. But this model had some problems. So first off, the atomic line spectra suggest that there are discrete amounts of energy, discrete quanta of energy that are gained or lost by the electrons. And that doesn't really make sense from a planetary model. Why should that be the case? Second, according to classical physics, electrons flying around the nucleus should be emitting radiation and slowly spiraling into the nucleus. And that doesn't happen. Atoms wouldn't be stable if that did. So there were some clear problems with this planetary model. So Bohr decided to borrow Planck's idea of quantization and build a model that could explain the hydrogen atom and predict the atomic line spectra. So to build his model of the hydrogen atom, Bohr ended up making two key assumptions. First, he said that the electron orbits must be stable, and so he worked out what physics was required to make them stable. And second, he used this idea of quantization, but instead of quantization of energy like we'd had in the Planck model and the photoelectric effect and so on, he said that the angular momentum was quantized, as the momentum of the electrons spinning around the nucleus was in some fashion quantized. So only specific values of the angular momentum L were going to be allowed. Those that were n times h over 2 pi. So h again is Planck's constant. 2 pi factors occur a lot when dealing with angular quantities, and n are these integers, 1, 2, 3, etc., that are doing the quantization. Neither of these assumptions was justified under classical physics, but again, he was trying to build a model that worked, just like Einstein, the photoelectric effect, and Planck in the black body radiation. And so using these assumptions, he was able to derive a model that gave energies and radii for the different possible orbits. The energies of each orbit were given by this: negative times this constant times 1 over n squared, and the radii of that orbit was given by a different constant times n squared. And so the innermost orbits have the smallest radii, and then as we go to higher n values, we get larger and larger radius orbits. Conversely, the energy of the innermost one ends up being the most stable, and the energy increases, that is, becomes less negative as we head to higher n values. So let's take a closer look at these Bohr model energy levels. So here again is my Bohr atom with the different orbits of different radii. Again, n equals 1 is the innermost orbit, and as n increases, the radius of the orbit increases. And as we saw from the energy expression on the previous slide, the energy is negative, but it becomes less and less negative as n gets larger, and it goes like 1 over n squared. And so we first see that the ground state is going to be the n equals 1. So the ground state is the most stable state, most stable orbit for the system. So if n equals 1, the energy is minus 2.178 times 10 to the minus 18 joules. So this is the lowest energy possible state that the electron can be, and it has the electron flying around in this orbit. However, there are a number of other possible states for the electron. The electron could also be in any of these other possible orbits. These orbits, however, have higher energies that we can obtain, for example, by plugging in n equals 2, or n equals 3, or n equals 4 in here. And if we do that, we'll compute these different possible n values. And so we call all of these higher lying orbits excited states. If the electron is in one of these, it's in an excited state. The other thing you'll notice, just because of the nature of the way the energy goes like 1 over n squared, the energy spacing decreases as we get to higher and higher values of n, higher and higher energy orbits. So the largest energy spacing occurs between n equals 1 and 2. It's smaller than between 2 and 3, smaller yet again between 3 and 4, etc. If we go all the way to n equals infinity, we're going to get an energy of 0. So the negative sign in the energy here corresponds to the fact that there's an attraction between the electron and the nucleus because they have opposite charges. The electron is negatively charged, the nucleus is positively charged, and those two things attract one another. However, as we go to further and further outlying orbits, as n gets larger, the interaction, the strength of the attraction between the electron and the nucleus is going to weaken. If we pull them far enough apart, they will eventually stop interacting. So as n goes to infinity, those electron and nucleus are so far apart that they have no interaction, that the energy is going to 0. And that corresponds to ionization, pulling the electron out of the atom such that it is no longer interacting with the nucleus. And so again, you can see that as we go to higher and higher n, the energies are decreasing, and eventually as n goes to infinity, we get to the limit of 0 interaction between the electron and the nucleus, and the electron is then ionized. Transitions between the different orbits in the hydrogen atom can occur through the interaction of the atom with light in the form of photons. So one possibility is absorption, where the atom is gaining energy from an incoming light. So we're shining light on the hydrogen atom, that energy is being absorbed and causing an excitation of the electron from a low energy orbit to a higher energy one. So for example, we might start out in the ground state, the n equals 1 state with our electron, and then if we hit it with a photon, we could potentially excite it up to, for example, the n equals 2 state. In order to do so, we need to look at the energy difference between the two orbits. So the difference between these two orbits, for example, is 1.6 times 10 to the minus 18 joules. That's just the energy difference between the n equals 1 state at negative 2.178 times 10 to the minus 18 joules and the n equals 2 state at minus 0.545 times 10 to the negative 18 joules. So if we hit the hydrogen atom with a photon with that amount of energy, that can be absorbed and excite the electron from n equals 1 up to n equals 2. And because we're adding energy into the system, raising up to a higher energy, the energy change in the system is positive. In contrast, we can also have emission, in which case we fall from a higher lying state, from an excited state, down to a lower energy state. Maybe the ground state, maybe just to a less excited state. And so, for example, in what I'm showing here, we are falling from the n equals 2 state to the n equals 1 state. In doing so, we must give off this amount of energy, again corresponding to the energy difference between these two states. That energy difference is negative because the energy is leaving the system, and the photon of light being emitted will have the energy content associated with this delta E. And to be clear, the absorption and emission can occur between any two orbits in a hydrogen atom, not just two adjacent ones. So for example, we could have emission from the n equals 3 to the n equals 1 state, as I'm showing here. The delta E, computed as the energy difference between these two orbits, works out to minus 1.9 times 10 to the minus 18 joules. So this is a slightly higher energy transition than the 2 to 1 transition that we looked at in the previous slides. The photon of light emitted here will therefore have this higher energy content, a higher frequency, or a shorter wavelength compared to the last example. The photon must always exactly match the energy difference between the two states involved. whether we're talking absorption or emission. In emission, the energy difference will determine the color of the photon coming out, its frequency or wavelength, and therefore its energy content. Or for absorption, the transition that occurs will be determined by what the energy content of the photon coming in is. But the key point here is that because the orbits are quantized, because there are only certain discrete orbits allowed, we are therefore only going to have certain possible transitions. Let's try a practice problem. Classify each of the following hydrogen atom transitions as either an absorption or an emission event. So first, we have a transition from the n equals 4 orbit to the n equals 2 one. Second, we have a transition from the n equals 1 orbit to the n equals 3 orbit. And third, we have a transition whose delta E is plus 2.0 times 10 to the minus 18 joules. So go ahead and try to classify each one of these, and then resume the video to hear the solution when you're ready. Okay, so the key thing to remember in working this problem is that emission occurs when an electron falls from a higher energy orbit down to a lower energy one, and the energy change is therefore negative. Absorption happens when the electron jumps from a lower energy orbit up to a higher energy one because it's absorbed a photon of light and absorbed the energy from that photon. And so, for example, if we look at the n equals 4 to n equals 2 transition, we're starting in this higher energy n equals 4 orbit and we're falling down to the n equals 2 one. So that's going to be an emission. For the n equals 1 to 3 transition, we're rising from a low energy orbit up to a higher energy one, and that's therefore absorption. It's going to require the input of energy from light to excite from n equals 1 up to n equals 3. For this third example, with delta E equals plus 2 times 10 to the minus 18 joules, we're gaining energy in the system. So we're moving up from a low energy one up to a higher energy one. It turns out in this case that this particular example corresponds to the n equals 1 to 4 transition. So we're absorbing light and going from n equals 1 to n equals 4. We previously said that the energy of the photon must exactly correspond to the energy difference between the two states involved in our absorption or emission. How do we actually compute the frequency of light that's required in order to have that absorption or emission? So what we're going to do is first we're going to compute the energy difference between the two orbits, which I'm calling here delta E orbits. So that's the energy difference between the final orbit and the initial orbit. Now the energy of the orbits is given by this expression here, minus 2.178 times 10 to the minus 18 joules times 1 over n squared. And since this is our final orbit, I'm calling this n final squared, minus the energy of the initial orbit, which is exactly the same, except I'm plugging in the initial value of n in here. I can simplify this expression a little bit and get this expression here, where it's equal to negative 2.178 times 10 to the minus 18 joules times 1 over n final squared minus 1 over n initial squared. So I just factored out the constant in front. And so using this expression, you can calculate the delta E between orbits. Alternatively, you can do like we've done in the earlier slides, where you just calculate the energy of each orbit separately and then go ahead and take the energy difference. It doesn't really matter how you do it. Once you know the energy difference between the orbits, then we can figure out what must the energy of the photon be that matches that. And so the energy of the photon has to be exactly the same, and the energy of the photon in terms of frequency is given by E photon is equal to h nu. So we have our delta E of orbits. We're going to set that equal to the photon energy, and the photon energy is going to be determined by the frequency via h nu, or the wavelength via hc over lambda. And so we can now use this expression to solve for the frequency or the light absorbed. So to recap, we're going to calculate delta E between the two orbits, and then we're going to set that equal to the photon energy h nu, or hc over lambda, and solve for nu, or solve for lambda. Let's try a practice problem with this. So, what wavelength of light must be absorbed to excite the hydrogen electron from the n equals 2 orbit up to n equals 3? So the transition shown in the figure here. Is it a 365 nanometer light, a 483 nanometer light, a 657 nanometer light, or an 821 nanometer light? And here are some expressions that will be useful in solving for this. Go ahead and attempt this problem and hit resume when you're ready to hear the solution. Okay, to solve this, again, what we want to do is we want to figure out what is the energy difference between the two orbits, and then figure out, in this case, the wavelength of light that's associated with that energy difference. So first, I'm going to calculate delta E orbits between the n equals 2 and n equals 3 orbits. So I'm going to use the expression we derived on a couple slides back, where delta E orbits is equal to minus 2.178 times 10 to the minus 18 joules times 1 over the n final squared minus 1 over n initial squared. In this case, n final is 3, n initial is 2, so I can plug those values in and I can crunch these numbers together in my calculator, and I find that the delta E between these two orbits is about 3 times 10 to the minus 19 joules. Now I know the energy difference between the two orbits, so I can go ahead and calculate what frequency of light is required to do this transition, or in this case, what wavelength of light is required to do the transition. And so we want the energy difference between the orbits to match the photon energy, which is either h nu or hc over lambda. In this case, I care about the wavelength, so I'm going to use the hc over lambda form. And I'm going to solve this expression for lambda. So in doing that, I get lambda is equal to hc divided by delta E orbits. And now I can plug in Planck's constant h, the speed of light c, and the energy difference between the orbits, and you'll notice that all my units canceled properly. I have the seconds here canceling the inverse seconds in the speed of light. I have the joules here canceling the joules in the denominator, and I'm going to be left with just units of meters. When I go ahead and crunch all these numbers in my calculator, I get 6.57 times 10 to the minus 7 meters. If I want to convert that to nanometers, I can use the conversion that there's 10 to the 9th nanometers per meter. And when I multiply this out, I get an answer of 657 nanometers, which corresponded to answer C. Now that we understand how transitions between the orbits work, let's look at how we can use the Bohr model to explain the hydrogen atom emission lines that are observed experimentally. So each one of these lines observed in the emission spectrum corresponds to a specific transition between two orbits. And there's a number of series depending on which part of the electromagnetic spectrum you look at, and they've each been given names based on the person who discovers them. So for example, the Balmer series is the name given to the set of transitions that occur in the visible light region. And so we have sort of purple, blue, all the way to red transitions for the hydrogen atom in this visible region. To understand these, we can just look at this diagram here, which shows that these Balmer series transitions all correspond to transitions from, for example, n equals 3, 4, 5, 6, etc., down to the n equals 2 state. So all of these ones here in the Balmer series are transitions that occur from emitting from a higher energy state down to n equals 2. The so-called Lyman transitions are ones that occur from higher lying values down to n equals 1. The Paschen series are those that end in the n equals 3 state. So you get these different groups of transitions depending on which final state you end up in. Finally, we can look at, can we use the Bohr model to describe atoms beyond hydrogen? And the answer is only partially, in a very limited way. It turns out the Bohr model can only describe one electron atom. So hydrogen obviously has one electron. You can also have one electron atoms by forming ions of some of the heavier ones. So for example, helium plus, lithium 2 plus, etc. And so in those cases, you can rederive the Bohr model And the only change is that you get a factor of z and z squared in the energies and orbits of your radii. So where z is the atomic number of the element. So for example, the energies look the same as the energies for our hydrogen except multiplied by z squared. The radii are going to be the same as before except divided by z. And z is, as we said, the atomic number. So for hydrogen, z equals 1. For lithium, 2 plus, for example, or any lithium ion, z would equal 3. However, the real problem with the Bohr model is that it can't be adapted to describe any system with 2 or more electrons. So that really rules out almost all of chemistry. So the Bohr model was a really good attempt at understanding what's going on the atoms, and it made clear progress in terms of being able to explain the hydrogen atom and the emission lines, but it's clearly not a universal theory. It's a band-aid, and we need a new theory that's something that can describe all of chemistry in a single approach. So to summarize, we've discussed how the Bohr model places the electron in one of many possible discrete orbits, and each of those orbits has its own specific radius and energy given by these expressions here. An electron can transition between two orbits via interactions with light. So an absorption of light will cause a transition from a lower energy orbit to a higher energy one, and emission of light will cause a transition from a higher orbit down to a lower energy orbit. The energy content of the light, E photon, must exactly match the energy difference between the two orbits, delta E orbits, as we've seen here. So we calculate the energy difference between our final and initial orbits to get delta E orbits, and we calculate the energy of the photon using h nu or hc over lambda, and these two must be equal for the transition to occur. And we said that we can use the Bohr model to describe the emission spectrum or absorption behavior of any one electron atom, hydrogen, helium plus, lithium 2 plus, etc., but it cannot describe any multi-electron atoms.